Okay, good afternoon, everybody. I found only 8 students attend the class. Let's wait for a while. Okay, last time we have learned about CRC code. CRC calculation is important. We should understand how to calculate CRC code. This figure illustrates the calculation for a bit stream 11010111 using the generator polynomial gx, x4 plus x plus 1, and under this generator polynomial, we can calculate the CRC code. CRC code is CRC code is 0 0 0 1 0. So we append 0 0 1 0 after the original frame. Okay, this is original frame. This is CRC code. CRC code means the remainder under this generator. So how to calculate? We should understand that we use XOR. That means if the 2 bits are different, we get 1. If two bits are same, we get 0. So 0, 0 gets 0. 1, 1 gets 0. 0, 1 or 1, 0, we get 1. So different. 2 bits are different, we get 1. 2 bits are same, we get 0. So it is very simple, but we should know we use XOR calculation. Then we can get the remainder 0, 0, 1, 0. So get the CRC. This we reviewed CRC calculation. Okay. Then we have learned elementary data link protocol. Elementary data link protocol, that means we have the assumption that machine A wants to send a long stream of data to machine B using a reliable connection-oriented service. We assume that machines do not crash. When the data link layer accepts a packet, it encapsulates the packet in the frame by adding a data link header and a trailer to it. Encapsulate the packet. And the frame is then transmitted to the data link layer on the other machine, and using these library interface functions. To physical layer to send frame, from physical layer to receive a frame. We just assume we can send a frame using by calling the to physical layer interface function. We assume that we can receive a frame by calling the function from physical layer. So this fig shows some declaration come to many of the protocols to be discussed later. 5 data structures are defined. Boolean, sequence number, packet, frame kind, and frame. Use this. I'm not sure whether you have the textbook. So you can buy textbook from the internet. And if you have, you can download the electronic version from the network or buy a paper edition. Then we introduced the first utopian simplex protocol. It is unrealistic because it does not handle either flow control, and error correction. Its processing is close to that of an unacknowledged connectionless service that relies on high layers to solve these problems, though even an unacknowledged connectionless service would do some error detection. The second protocol we introduced that is a simplex stop and wait protocol for an error-free channel. Error-free channel, that means the channel does not lose packets. Now we tackle the problem of preventing the sender from flooding the receiver with frames faster than the latter is able to process them. That means this kind of protocol have the function of flow control. Communication channel is still assumed to be error-free, means the channel is reliable. So the frames will not be lost by the channel. However, the data traffic is still simplex. The general solution to this problem is to have the receiver provide feedback to the sender. After having passed a packet to its network layer, the receiver sends a little dummy frame back to the sender, which in fact gives the sender permission to transmit the next frame. After having sent a frame, the sender is required by the protocol to bide its time until the little dummy frame arrives. This delay is simple examples of a flow control protocol. Protocol in which the sender sends one frame and then waits for the acknowledgement before proceeding are called stop and wait. This figure shows an example of a simplex stop and wait protocol. This is a structure, a variable definition. Then we have two functions. One is for sender, one is for receiver. Then the while true means this sender can transmit the frames again and again. That means the sender have much information to send. The means from step one from network layer means data link layer gets a packet from the network layer. This sentence means the data link layer encapsulates the packet into a frame. S, what's the S? S dot s dot information. Here s, right? Here s is a variable. Is type. Type is a frame. Is a frame. Frame s. That means s is a variable of the type frame. So encapsulate the packet, gets a packet from the network there, and set the and put the packet into a buffer, right? Then put the buffer. That means put the packet into a frame S. Then next step is transmit the frame to the physical channel, right? The physical channel. The physical channel, then the sender should wait for event, means wait for acknowledgement from the receiver. Wait for events. These events, what is the event? Event means here, event type, event, right? Here, the event. The event type, we have this type, frame arrival. Frame arrival. That means acknowledgement frame arrived at the sender. So this is the sender, right? Then let's look at the receiver. Receiver, while true, means the receiver can receive the frame from the sender again and again. Then wait for events. Wait for events. Event means this event. That means a frame arrive to the receiver. The event frame arrival means a new packet arrived. So wait for a new packet arrived from the sender. Then the wait for events. Then this sentence from physical layer means the data link layer gets or receive a frame from the physical channel and put the frame into the variable R. R here, R is a frame, right? The frame type. Then next sentence, to network layer means the data link layer gets the packet from the payload of the frame and put the packet into the payload of the R. Put the frame, put the packet or deliver the packet to the network layer. Then last sentence is to physical layer means the data link layer reply an acknowledgement to the sender. Then the sender can continue to send next frame. Okay. Then let's consider the normal situation of the communication channel that make errors. That means the channel may be noisy, may not reliable. So frames may be either damaged or lost completely. However, we assume that if a frame is damaged in transit, the receiver hardware will detect this when it computes the checksum. When the acknowledgement frame gets lost completely, the data link layer on the machine A eventually times out. The duplicate frame may arrive intact at the data link layer on machine B. The receiver be able to distinguish a frame that is seen for the first time from a transmission. So the duplicate frame can be determined. The obvious way to achieve this is to have the sender put a sequence number in the header of each frame it sends. Then the receiver can check the sequence number of each arriving frame to say if it is a new frame or a duplicate be discarded. And only one bit sequence number can be used in the sequence number. So a 1-bit sequence number is sufficient. This figure 14 shows an example of this kind of protocol. It is more complex. More complex. Okay, you can read this figure shows the example of the stop and wait protocol for noisy channel. While true S-info, that means put a packet buffer. Yes, buffer means packet variables, packet variable buffer, right? So put the packet into a frame or encapsulate a packet into a frame. Then set the sequence number for this frame to be transmitted. Then transmit the frame to the physical channel by calling the function toPhysical_layer. Then after transmit this frame, the sender set the timer out for the sequence number frame, for the frame with the sequence number SEQ. Then wait for an event which is acknowledgement for this frame from the receiver. Then, if an event arrived, then the sender will jump out from the block, then continue to run the following sentences. So if the event is frame arrival, then receive a frame from physical layer by calling this function. And then if the sequence number, if the AC key number is the next frame to send, then stop timer. And get a new packet from the network layer and increase the next frame sequence number to send. Then continue the loop. This is what the sender do. Then how about the receiver? Receiver here, while true, then wait for event. Wait for event. Wait for event means wait for a new packet arrived at the receiver. If the event is a frame arrival, then received a frame from the physical channel. And if the sequence number is the frame expected, then received the frame. First, get the packet and deliver the packet to the network layer and increase the frame expected. That means expected next frame to arrive. If the sequence number is not the frame expected, then set SACK number as the 1 minus frame expected. That means if the frame expected is 0, then ACK is 1. If the frame expected is 1, then the ACK is 0. Then transmit the frame to the physical channel. That is what the stop and wait protocol for noisy channel. Protocols in which the sender waits for a positive acknowledgement before advancing to the next data item is often called ARQ. or PAR. ARQ means automatic repeat request. PAR means positive acknowledgement with retransmission. Then usually flow control depends on sliding window protocol. In this model, the data frames from A to B are intermixed with the acknowledgement frames from A to B. When a data frame arrives, instead of immediately sending a separate control frame, the receiver restrains itself and waits until the network layer passes it, the next packet. Acknowledgement is attached outgoing data frame using the ACK field in the frame header. In fact, the acknowledgement gets a free ride on the next ongoing data frame. The technique for temporarily delaying outgoing acknowledgements so that they can be hooked onto the next outgoing data frame is known as piggybacking. The essence of all sliding window protocol is that at any instant of time, the sender maintains a set of sequence numbers corresponding to the two frames is permitted to send. These frames are set to fall within the sending window. Similarly, the receiver also maintains a receiving window corresponding to the set of frames it is permitted to accept. The sender's window and the receiver's window need not have the same null and upper limits, or even have the same size. In some protocols, they are fixed in size, but in others they can grow or shrink over the course of time as frames are sent and received. The sequence numbers within the sender's window represents frames that have been sent or can be sent but are as yet not acknowledged. Whenever a new packet arrives from the network layer, it is given the next highest sequence number, and the upper edge of the window is advanced by 1. When an acknowledgement comes in, the null edge is advanced by 1. In this way, the window continuously maintains a list of unacknowledged frames. So, sliding window continuously maintain a list of unacknowledged frames. So if a frame is acknowledged by a reply, then this frame can be removed from the sliding window. So sliding window continuously contains a list of unacknowledged frames. This figure shows the sliding window example. A sliding window of size 1 with a 4-bit sequence number. We know With a 3-bit sequence number, we can have 8 numbers for number of windows. The subfigure A shows the initial states of the window. Subfigure B shows after the first frame has been sent. C shows after the first frame has been sent. And after D, after the first acknowledgement has been sent, has been received. So then we will give some examples later. So we will not discuss in detail. We should discuss this sliding window with some examples. Then protocol 3 is a kind of 1-bit sliding window protocol. Before tackling the general keys, let's examine a sliding window protocol with a window size of 1. And such a protocol uses stop and wait since the sender transmits a frame and waits for its acknowledgement before sending the next one. So this figure shows the 1-bit sliding window protocol. Okay. Then we will talk about a protocol using go back N mechanisms. Until now, we have made the tacit assumption that the transmission time required for a frame to arrive at the receiver plus the transmission time for the acknowledgement come back is negligible. Sometimes this assumption is clearly false. In these situations, the long round-trip time can have important implications for the efficiency of the bandwidth utilization. As an example, consider a 50 kbps satellite channel with a 500 milliseconds round-trip propagation delay. Only 4% of the available bandwidth was used. The problem described here can be viewed as a consequence of the rule requiring a sender to wait for an acknowledgement before sending another frame. If we relax that restriction, much better efficiency can be achieved. Basically, the solution lies in allowing the sender to transmit up to W frames before blocking instead of just 1. When a large enough choice of W, the sender will be able to continuously transmit frames since the acknowledgements will arrive for previous frames before the window becomes full, preventing the sender from blocking. To find an appropriate value for W, we need to know how many frames can fit inside the channel as the propagation from the sender to receiver. So this capacity is determined by the bandwidth in bits per second multiplied by the one-way transmit time, or the bandwidth delay product of the link. So for small window sizes, the utilization of the link can be less than 100%, since the sender will be blocked sometimes. We can write the utilization as the fraction of time that a sender is not blocked. Using this equation. This figure shows the sliding window shows a protocol using go-back-N mechanisms. Two basic approaches are available for deadline with errors in the presence of pipelining, both of which are shown in the figure 18. So we assumed frames 1, 0 arrive at the receiver normally, but the E frames has an arrow, and the frames after frame E will be dropped. Frames discarded by data link layer. So since the frame E has an arrow, so the frames after E, the acknowledgement should be NAK frames arrived. Non-acknowledgements are transmit to the sender. Okay, let's have a rest for 10 minutes. Please keep connection. Have a rest for 10 minutes. Okay. Okay, last session we introduce, we assume that here is a frame because arrow, then one option called go back n is for the receiver simply discuss all subsequent frames, discard all subsequent frame, right? Sending no acknowledgements for the discarded frames. This strategy corresponds to a receive window of size 1. In other words, the data link layer refuses to accept any frame except the next one. It must gives to the network layer. If the sender's window fills up before the timer runs out, the pipeline will begin to empty. Eventually, the sender will time out and retransmit all unacknowledged frames in order, starting with the damaged or lost one. This approach can waste a lot of bandwidth if the error rate is high, because many frames arrived normally after the arrow frame will be discarded. So if the error rate is high, then this approach can waste a lot of bandwidth. Figure 18 for the case in which the receiver's window is large. Okay, we will not illustrate it. Then the improved version of go back n is a selective repeat, using another general strategy for handling errors when frames are pipelined. When it is used, a bad frame that is received is discarded, but any good frames received after it are accepted and buffered. It is different from the first one. First one means the receiver simply discards all subsequent frames, sending no acknowledgements for the discarded frame. But the selective repeat version, the improved go back n protocol, says a bad frame is received is discarded, but any good frames received after it are accepted and buffered. When the sender times out, only the oldest unacknowledged frames is retransmitted. If that frame arrives correctly, the receiver can deliver to the network layer in sequence all the frames it has buffered. Selective repeat corresponds to a receiver window larger than 1. This approach can require large amounts of data link layer memory if the window is large, because the The consecutive good frames should be buffered in the memory, so need not require large amounts of data link layer memory. The go-back-N protocol works well if errors are rare. That means the channel has a very low error rate. But if the line is poor, it wastes a lot of bandwidth on retransmitted frames. An alternative strategy, the selective repeat protocol, is to allow the receiver to accept and buffer the frames following a damaged or lost one. In this protocol, both sender and receiver maintain a window of outstanding and acceptable sequence numbers, respectively. The sender's window size starts out at 0 and grows to some predefined maximum. So the receiver's window, in contrast, is always fixed in size and equal to the predetermined maximum. Here, the figure 22 illustrates the selective repeat protocol. So figure A shows an initial situation with a window of size 7. From 0 to 6 means frames with the sequence number 0, 1, 2, 3, 4, 5, 6 here. These 7 frames can be transmit, and these frames can be received by the receiver. Subfigure B shows that after 7 frames have been sent and received, but no acknowledged. Subfigure C shows the initial situation with a window size of 4. D shows after 4 frames have been sent and received, but not acknowledged. Okay, and this selective repeat we are not talk about in detail. Then we will analyze some other protocols with some examples, such as homework or exercises. Okay, we will not discuss the other protocols. So in this chapter, we talk about data link layer design issues, error detection, flow control with sliding window. Then we will continue the next chapter. Next, Chapter 4, Chapter 4. Chapter 4 is about medium access control sublayer. Chapter 3, data link layer. Chapter 2, physical layer. Right? Chapter 1 for the architecture reference model. This chapter has these knowledge points. Channel allocation problem, multiple access protocols, Ethernet, wireless LANs, broadband wireless, Bluetooth, RFID, and data link layer switching. So we will focus the channel allocation problem and multiple access protocols for Ethernet and wireless LANs. And from 5 to 8, and that's the 4 points we will not talk about in detail. So the key points is from 1 to 4. Network links can be divided into 2 categories. Those using point-to-point connections, and those using broadcast channels. So one is a point-to-point, right? And the other using broadcast channels. The broadcast channels are sometimes referred to as multi-access channels or random access channels. In any broadcast network, the key issue is how to determine who gets to use the channel when there is a competition for it. That means many users want to use the channel. Then the protocol should determine which one gets to use the channel. The protocols used to determine who goes next on multi-access channel belong to a sublayer of data link layer called the MAC sublayer. Means medium access control sublayer. The MAC sublayer is especially important in LANs, particularly wireless ones, because wireless is naturally a broadcast channel. So in any broadcast channels, we need MAC sublayer to determine which user grasp the channel. So we will focus on the channel allocation problem. The central theme is how to allocate a single broadcast channel among competing users. Channel might be a portion of the wireless spectrum in the geographic region, or a single wire or optical fiber to which multiple nodes are connected. There are 2 types of channel allocation schemes. One is static, the other is dynamic. At first, we talk about the static channel allocation. The traditional way of allocating a single channel such as a telephone trunk. Telephone trunks, the cable connect one switch office to another switch office. Among multiple computing users is to chop up its capacity by using FDM, etc. FDM, frequency division multiplexing, or TDM or CDM, etc. If there are n users, means the number of users is n. The bandwidth is divided into n, capital N, equal-sized portions. So with each user being assigned one portion, then we assumed the bandwidth, the total bandwidth of the channel is capital B. The total bandwidth is B, then there are n users, right? So each user has a private frequency band. There is now no interference among users. That is why we call it static channel location. However, when the number of senders is large and varying or the traffic is bursty, FDM presents some problems. If the spectrum is cut up into n regions and fewer than n users are currently interested in communicating, a large piece of valuable spectrum will be wasted. Dividing the single available channel into some number of static subchannels is inherently inefficient. That means static channel allocation has very low utilization. Static allocation is a poor fit to most computer systems. The poor fit to most computer systems, okay, in which data traffic in the computer systems, data traffic is extremely bursty, right? So often with peak traffic to mean traffic ratios of 100 to 1. Consequently, most of the channels will be idle most of the time. So the static allocation is not suitable to the computer communication at all. Further, the poor performance of static FDM can easily be seen with a simple Queen theory calculation that starts by finding the mean time delay denoted by capital T to send a frame onto a channel of capacity C bps, bit per second, bps. We assume that the frames arrive randomly with an average arrival rate of lambda frames second, and that the frames vary in length with an average length of 1/mu bits. So with this, here mu is here mu, okay. Here mu is less than 1. So 1/mu bits. With these parameters, the service rate of the channel is mu times capital C frames per second. Standard Queen theory. So probably you are not familiar with the Queen theory. Queen theory is a mathematical tools to analyze the communication system. Depend on this Queen theory, a standard Queen theory result can be obtained by this equation. The mean delay t, equals 1/mu c minus lambda. Now let's divide the single channel into n independent subchannels, each with capacity C divided by n bps. The mean input rate on each of the subchannels will now be this. Recomputing T, we get Tm. Here Tm means divide into n independent subchannels. In this situation, we get a new delay. So here Tm equals n, so we get n times t, right? N times t. That means the mean delay for the divided channel is n times worse than if all the frames are somehow magically arranged orderly in a big central key. So the subchannels, precisely the same arguments that apply to FDM also apply to other ways of statically dividing the channel. So this result tells us that static division is not good scams, since none of the traditional static channel allocation methods works well. So none of the traditional static channel works well at all with bursty traffic. Here, bursty traffic is the key characteristics of most computer system communication. So computer communication has the characteristics of bursty, but traditional traffic channel, none of the traditional channel works well for computer communication with burst traffic. So we will now explore dynamic methods. So we now explore dynamic. So how dynamic methods are? Before we get to the first of the many channel allocation methods in this chapter, it is worthwhile to carefully formulate the allocation problem. Underlying all the work done in this area are the following 5 key assumptions. 5 key assumptions. 1. Independent traffic. Frames arrivals are independent, both across stations and at a particular station, and that frames are generated unpredictably but at a constant rate. So that is what is the independent traffic means. Second, single channel. A single channel is available for all communication. Why a single channel? We assume single channel used because because dividing the channel into sub-channels is not good, it's not suitable for burst traffic. So we turn to a single channel. Is available for all communication. All stations can transmit on it, and all can receive from it. The third point is observable collisions. Collision. What is the collision? If 2 frames are transmitted simultaneously at the same time, 2 frames are transmitted at the same time, they overlap in time, and resulting signal is garbled. This event is called a collision. They overlapped in time. The electromagnetic wave overlap for 2 frames. So the event is called a collision. All stations can detect that a collision has occurred. A collided frame must be transmitted again later. No errors other than those generated by collision occurs. The fourth point of assumption is continuous or slotted time. Time may be assumed continuous, in which case frame transmission can begin at any instant. So if we assume the time continuous, in this case, frame transmission can begin at any instant. Alternatively, slotted time. Alternatively, time may be slotted or divided into discrete intervals called slots. Frame transmissions must then begin at the start of a slot. A slot may contain 0, 1, or more frames, corresponding to an idle slot, a successful transmission, or a collision, respectively. Next point is carrier sense or no carrier sense. With the carrier sense assumption, stations can tell if the channel is in use before trying to use it. So when with the carrier sense, stations can tell if the channel is in use before trying to use it. That means if the channel is in use, the station knows. And before trying to use it, the station will hear from the channel. So, no station will attempt to use the channel while it is sensed as busy. If there is no carrier sense, stations cannot sense the channel before trying to use it. They just go ahead and transmit. Only later can we determine whether the transmission was successful. So, carrier sense or no carrier sense. We know carrier sense assumptions helps to improve the efficiency of the channel. So carrier sense is better than no carrier sense. Because if without a carrier sense, the station does not know whether the channel is in use before trying to use it. Only later can they determine whether the transmission was successful. It will waste some bandwidth of the channel. Now, to avoid any misunderstanding, it is worth noticing that no multi-access protocol guarantees reliable delivery. Even in the absence of collision, the receiver may have copied some of the frames incorrectly for various reasons. So, to avoid any misunderstanding, it is worth noting that no multiple access protocol guarantees reliable delivery. So even in the absence of collision, the receiver may have copied some of the frames incorrectly from various reasons. So other parts of the link layer or higher layers provide reliability. Then we will introduce the basic MAC protocols named Aloha. The first MAC starts out in the Princeton, Hawaii in the early 1970s due to a researcher named Norman and his colleagues at the University of Hawaii who were trying to connect users on remote islands to the main computer in this place, Honolulu. In this case, precedent can be interpreted as not having a working telephone system or not having any communication infrastructure. So no network. So the one solution we found used short-range radios, with each user terminal sharing the same upstream frequency to send frames to the central computer. It included a simple and elegant method to solve the channel allocation problem. Although his work called Aloha System used ground-based radio broadcasting, the basic idea is applicable to any system in which uncoordinated users are computing for the use of single shared channels. Aloha has two versions. One is pure Aloha, and the other is slotted Aloha, slotted time Aloha. For example, just now we talk about continuous or slotted times. Two versions. One is continuous, the other is slotted. So the Aloha has two versions. One is pure Aloha, the other is slotted Aloha. They differ with respect to whether time is continuous, as in the pure version, or divided into discrete slots into which all frames must fit. So why times can be looked as continuous or time slot? In our real life, the time is actually continuous. But in computer systems, we can look at the time, we can process the time with different methods. Divided into, for example, divided in the time into discrete slots into which all frames must fit. So the first version, pure Aloha, means the continuous time Aloha, pure Aloha. The basic idea is simple. Net users transmit whenever they have data to be sent. There will be collisions, of course, and the colliding frames will be damaged. In the Aloha system, after each station has sent its frame to the central computer, this computer rebroadcasts the frames to all of the stations. A sending station can thus listen for the broadcast from the hub to see if its frames has gotten through. If the frames was destroyed, the sender just waits a random amount of time and sends it again. The waiting time must be random, or the same frames will collide over and over in locksteps. Systems in which multiple users share a common channel in a way that can lead to conflicts are known as contention systems. the contention system, because multiple users competed using the system, using competition to use the channel. So it's known as contention system. This figure shows the pure aloha principles of pure aloha. A sketch of frame generation in the aloha system is given in the figure 1. We have made the frames all the same length because the throughput of aloha system is maximized by having uniform frame size rather than by allowing variable length frames. So whenever two frames try to occupy the channel at the same time, there will be a collision and both will be gobbled. Means has a collision, be overlapped. So there's an overlapped, right? This frame A, B, and D has overlaps. So there will be a collision among them. And in the pure aloha, frames are transmitted at completely arbitrary times. For example, these frames collision occurs between them. Now, an interesting question is, what's the efficiency of an aloha channel? In other words, what fraction of all transmitted frames is gap collision under these chaotic circumstances, since there are many collisions among the system, right? There are many. Since the frames are transmitted at a completely arbitrary time, that means there must be much collision. There are many collisions in the system, right? So an interesting question is, what is the efficiency of an aloha channel, of a pure aloha? In other words, what fraction of all transmitted frames is gap collisions? Those frames lucky to escape collision under these chaotic circumstances. So it is a very interesting question. How to get the result? We can analyze with the Queen system. We can get this result. So the maximum throughput occurs with about, in other words, the best we can hope for is a channel utilization of 18%. 18%. So it is not zero, right? It is not zero, not zero. The utilization of the channel is not zero. It is 18%. It's larger than zero. So the result is not very encouraging. It's not very encouraging, but with everyone transmitting at the well, we could hardly have expected to 100% success rate. It's very interesting. So next week, I will explain why we can get this efficient utilization. So much for today. Bye. So much for today. Bye.